Hi everyone, and it is a beautiful morning. I don't know whether you're listening to this in the morning or not, but the sun is shining. It's going to be a great day. In this video, we're going to go through 16B standardization and the 68, 95, 99.7% rule. So we're staying with normal distribution, and basically this section is very straightforward. Okay, if you understood 16A, you'll be fine with this. The 68, 95, 99.7% rule basically just tells us the proportion of a population that falls within 1, 2, 3 standard deviations of the mean. So, and you remember with normal distribution, your data does have to be symmetrical. So we always have to have a bell-shaped curve. It won't work if it's skewed data or skewed probability. Okay, so it has to have this bell-shaped curve. So what I've got on this first page are the three scenarios. So the first one is 68%. So let me just get my highlighter. So 68% is within one standard deviation. So you can see you've got your mean in the middle and you've got one standard deviation either side. Now this one has already been standardized, so we've got a mean of 0 and -1 and 1 either side, but you don't have to standardize it to work out the percentages. So when we do some questions, that'll make sense in a second. Okay, now you also need to know the percentages either side. Okay, because you're not just going to deal with a simple 68%. You need to know what percentages are either side of that. So we know everything has to be 100% from -infinity to infinity. So let's take away that middle 68% and we are left with 32%. Now that's not 32% either side. Okay, that 32% is divided by 2. So that means you have 16% either side. All right, so you do need to deal with these percentages as well, not just the 68%. So knowing that 16% either side is extremely important. All right, moving on to 95%. So this time we are 2 standard deviations either side. And the reason it's increasing is because we're looking at a larger part or a larger area. Okay, so you can see how your area has increased. And again, we do need to work out the percentages either side here. And 100 take away 95 is 5. 5 divided by 2, so that's 2.5% either side. All right, and lastly, we have 99.7% is 3 standard deviations either side of the mean. So you can see we're at -3 to 3. So the majority of the population, you can never do 100%, okay, because we are going from -infinity to infinity, but it's pretty close to 100%. All right, and we do need to do the percentages either side. Now, some students get these confused. All right, so 100 take away 99.7 leaves you with 0.3. 0.3 divided by 2 is equal to 0.15. So this is 0.15%. All right, so just have them written down so you can always refer to them. But the percentages aren't that difficult to remember. Although I always forget this last one. I always think of, is it 99.7 or 99.97? All right, it's 99.7. All right, those percentages are the easy ones. All right, sometimes you might have a question where you have to look at not necessarily one standard deviation either side, but you might have to go from, say, the mean to, one standard deviation above, so +1. All right, so you need to work out what that area is. Okay, so if we're looking at that area, and there's all different combinations, so it's just not this one. So when you're looking at either side of the mean, so this is 50%, and the other side is 50%. And then if we just want this section here, that's going to be 50% minus And if we scroll up to, oh, why are you still on the screen? That's not good. Computer's glitching. No, we'll just go up with you. You can see it's 16%. So it's very strange, isn't it? All right, so 50%. So the whole right side minus this 16% here will leave us with that. So what is that? 34%. All right, so I'm not going to do every combination because I just don't have time to do it, but do remember that you're going to have to play around with those percentages. And are you going to keep following me? All right, I don't know how to get that to stay, so I might just pause for a sec. Oh, there we go. All right, so let's jump into some questions. So the distribution of blood pressures among women of similar ages is normal with a mean of 120. So let's highlight that. So a mean of 120 and a standard deviation of 10. Determine the percentage of women with a systolic blood pressure, blah, blah, blah. Okay, so let's draw our normal distribution first. So whenever you do normal distribution, you should always just quickly draw your curve and then put your mean in the middle. Okay. And then your standard deviation either side. So we're going to always do 3 either side. So our standard deviation is 10, so I go up by 10 each time. So 130, 140, 150, and then down on the other side, 110, 100, 90. Okay, so for the first question, we want between 100, so we're here, and 140. So that one's quite easy because it's 2 standard deviations either side. So that's going to be 95%. All right, so 2 standard deviations either side is 95%. All right, I'm just going to stick with the same normal distribution. Greater than 130. So this time, I was going to hope the colors looked a bit different, but that orange looks pretty much like that pink. All right, this time we want this area greater than 130. So we're looking now at 130 is 1 standard deviation above. So this percentage here is 16%. If you're ever unsure, just scroll back up. Okay, so there it is there, 16%. All right, so we're at 16% here. Let's change the color, hopefully to a color that doesn't look exactly the same as the others. Let's do purple. All right, greater than 120. Oh, this one's easy because 120 is your mean, so it's 50% either side. And then let's do green. Okay, between 90 and 150. Oh, so this one's not too hard. We don't have too many different percentages. So that's 3 standard deviations from the mean. So it's 99.7%. You don't have to do any calculations. You can just get your answers from the 68, 95, 99.7% rule. Okay, so you're just playing around with them. That will apply for any distribution that is normal, that is symmetrical, where your mean is in the middle. All right, let's have a look at question 10. So the heights of women are normally distributed with a mean of 160 and a standard deviation of 8. All right, so let's first of all draw our bell-shaped curve. It doesn't take long to draw this curve, and visually it just makes it so much easier. So we're going 1, 2, 3, 1, 2, 3, and we're 8 standard deviations either side. So 168, 176, and then 184. Just make sure I've added that correctly, and then 152, 144, and 136. Just wanted to make sure that that was correct. Okay, so what is the standardized value? Oh, actually, we're not doing that. Sorry, I should have read the question first. It's actually asking for the standardized value, not the bell-shaped curve, but there's a bell-shaped curve for you. All right, so the standardized value. Oh, I've put this question in the wrong spot. Okay, that's me rushing and not thinking about the questions. All right, let's jump ahead quickly to this and then, all right, so this is your formula for the standard score. So the standard score just helps you compare groups, and when we do question 14, that will make more sense. But this is your formula. So the standardized score, we usually use the letter Z to represent. So X is your value minus your mean divided by your standard deviation. Okay, so let's quickly do that one. And I feel like I did the same with question 10, so I might have to just mix them around. All right, so your Z score formula, I'll just write again. Okay, so for question A, 160, so Z equals 160 minus your mean, which is 160, divided by your standard deviation. Now, 160 minus 160 is 0, so she would have a standard score of 0. So that means if anyone is reading or interpreting that Z score, this woman who is 160 centimeters tall is average. She is right on the mean. Okay, so that's what the 0 means. She's right on the mean. So if you're 160 centimeters tall, although I don't know how accurate this is because it would depend on, I guess, different populations and so forth. Okay, let's do 150. 150 minus 160 is negative 10 over 8. And then I probably should do that on the calculator. All right, so negative 10 over 8, negative 1.25. Okay, so this means this woman is below the mean. All right, she's just below 1 standard deviation from the mean. And because it's negative, it means you're below the mean, but you can also see that she is below the mean. She is shorter than 160 centimeters. All right, and then obviously we're going to have an example of someone who is taller, and you can safely assume that that's going to be a positive Z score, which means she's above the mean. So what's that, 12 over 8? Is that 1.5? Oops. Look at me, I'm just doing it anyway. There we go, 1.5. So she's 1.5 standard deviations above the mean. Now I'm about 178 centimeters. So let's say I was 176 centimeters. I would be 2 standard deviations above, which is here. So quite tall, okay? And you know that, okay? You know I'm quite tall. I don't think there's anyone taller than me in our methods classes, but you know, like basketballers would be about 184 centimeters or taller. So very tall people, and you can see positive would be above the mean. All right, let's just do question 11 as well, even though I thought it was a different type of question. So the length of pregnancy for a human is approximately normally distributed with a mean of 270 days and a standard deviation of 10. How many standard deviations away from the mean is a pregnancy of a length? Okay, so we still do the Z score for each one. So your Z score is X minus your mean over your standard deviation. All right, so for question A, so 256 minus 270. So I know that's going to be negative. So this woman gave birth early. So let's go 256 minus 270 divided by 10. Negative 1.4. All right, so she's just just a little bit over 1 standard deviation below the mean. 281, so this person has gone over their due date. All right, so that's 11 over 10. All right, so 1.1. And then C, 305 days. Oh my God, this baby's been cooked. long time in the oven. So 305 minus 270, was that 35 over 10? So 3.5. All right, so that's highly unusual. That's such a high standard deviation. Oh, not standard deviation, but quite a distance away from the mean. So very, very small population would be that. Just double checking that that is all right. Yes. Okay. All right, let's move on to the standard score. So that's what we were just basically doing. So standardized values, and I might just read this. Let me just get rid of that. Clearly, the standard deviation is a natural measuring stick for normally distributed data. For example, a person who obtained a score of 110 on an IQ test with a mean of 100 and a standard deviation of 15 is less than one standard deviation from the mean, so above the mean. Their score is typical of the group as a whole, as it lies within the middle 68% of scores. In contrast, a person who scored 133 has done exceptionally well. Their score is more than 2 standard deviations from the mean, and this puts them in the top 2.5%. So you can kind of think about it in terms of your ATAR score. Okay, you know that it's very rare for someone to get 99.95. All right, so it's, you know, that is the highest score you can get, and very few students get that score because, you know, the ATAR is normally distributed as well. So those top students, that's why, you know, it's very hard to get quite a high ATAR score, because at the end of the day, you're all put into a bell-shaped curve anyway. Okay, you can't all get 100%. And if you all got 100%, then, you know, the exams and the SACs aren't hard enough. All right, so because of the additional insight provided, it is usual to convert normally distributed data to a new set of units which shows the number of standard deviation. Each value lies from the mean of the distribution. So these new values are called standardized values, or we call them Z values, or if you do further maths, they're called Z scores. To standardize a data value X, we first subtract the mean of the normal random variable, and the value then divide blah, blah, blah. That's basically just this formula here, which we've just been using, okay? All right, so standardized values can be positive or negative, which we've just realized. So a positive Z value indicates the data is above the mean, okay? So remember, a tall person would have a positive Z score, and a negative Z score means you're below the mean. Doesn't mean that anything is better or worse, it just means where you fit in relation to the mean. All right, so question 14. All right, so I chose this one because you can see how you can use it to compare students. All right, so 3 students took different tests in French, English, and maths. Okay, so we've got Mary, Steve, and Sue. Determine the standardized scores for each student on the test. Okay, so the mean and standard deviation, oh, it's different. Why is it different for each class? Let me just think. Maybe it's for their class. Okay, so maybe Mary, Steve, and Sue are also in different French, English, and maths classes. Otherwise, they should have the same mean and standard deviation. All right, so let's just do the Z score for each one. Now remember, your Z score formula is this. All right, so X minus your mean divided by your standard deviation. So I'll just do the first one for Mary, and then I'm going to pause and just do the rest. Otherwise, you could be waiting for a while. Okay, so Z score for Mary in French. So her mark is 19. The mean was 15. Divided by 4, so that's 4 over 4, which is equal to 1. And we can see that Mary did better than the class, so you would expect a positive Z score. So her standard score there is 1. All right, so I'm going to go ahead and do the rest of them, and you might like to also pause and do the rest. All right, so there's your standard score. Sorry, it's a little bit wonky. So question B, who is the best student in French? Okay, so if you were to look at them without standardizing your scores, you might say, oh, well, Steve got the highest mark in French, he got 21, whereas Mary got 19 and Sue got 15. But let's say these students were from different schools and they sat a different test, okay, which is what happens with your SACs. So if you've got a friend at, say, St. Bede's and he does really well on his SACs and you're like, oh, you got 95%, I only got 80%, but your SAC could have been harder. All right, so standardizing them is extremely important. So if we look at the standard score though, Mary actually did better. She's got a standard score of 1, whereas both Steve got a negative standard score and Sue got the same as the mean, so 0. Okay, so who is the best in French? Probably Mary. She's got the better standard score. Who is best at English? So Mary also has the highest standard score at 0.875. Steve, he's got -1. Okay, so even though he got quite a high score like Mary and Sue, but compared to the rest of his class, he didn't do as well, whereas Mary did quite well. And then in maths, Steve got the highest standard score at 1.25, so he is the best student in mathematics. Who is the best student overall? Give reasons for your answer. So you can see Mary, she didn't get any negative Z scores. She did get 0 for maths. She got the same as the rest of the class. So you could probably say that she's the best student overall. Who is the worst? Probably Steve. Steve did quite well in maths. And Sue, Sue's pretty average. Yeah, so you can look at your standard scores and it kind of tells you a little bit more information about how the student compares to the rest of their class. And then, if you've got these students at different schools, then you can use your standard score to compare how they actually relate to each other. All right, girls, that's it. Bye.